The scientific revolution was the emergence of modern science during the early modern period, when developments in mathematics, physics, astronomy, biology and chemistry transformed views of society and nature. The scientific revolution began in Europe towards the end of the Renaissance period and continued through the late 18th century, influencing the intellectual social movement known as the Enlightenment. While its dates are disputed, the publication in 1543 of Nicolaus Copernicus's De Revolutionibus Orbium Coelestium is often cited as marking the beginning of the scientific revolution. A first phase of the scientific revolution, focused on the recovery of the knowledge of the ancients, can be described as the scientific renaissance and is considered to have ended in 1632 with publication of Galileo's dialogue concerning the two chief world systems. The completion of the scientific revolution is attributed to the grand synthesis of Isaac Newton's 1687 Principia, that formulated the laws of motion and universal gravitation. By the end of the 18th century, the scientific revolution had given way to the age of reflection. The concept of a scientific revolution taking place over an extended period emerged in the 18th century in the work of John Sylvan Bailey, who saw a two-stage process of sweeping away the old and establishing the new. Introduction. Advances in science have been termed revolutions since the 18th century. In 1747, Clairaut wrote that Newton was said in his own lifetime to have created a revolution. The word was also used in the preface to Lavoisier's 1789 work, announcing the discovery of oxygen. Few revolutions in science have immediately excited so much general notice as the introduction of the theory of oxygen. Lavoisier saw his theory accepted by all the most eminent men of his time, and established over a great part of Europe within a few years from its first promulgation, in the 19th century. William Whewell established the notion of a revolution in science itself that had taken place in the 15th–16th century. Among the most conspicuous of the revolutions which opinions on this subject have undergone, is the transition from an implicit trust in the internal powers of man's mind to a professed dependence upon external observation, and from an unbounded reverence for the wisdom of the past to a fervid expectation of change and improvement. This gave rise to the common view of the scientific revolution today. A new view of nature emerged, replacing the Greek view that had dominated science for almost 2,000 years. Science became an autonomous discipline, distinct from both philosophy and technology, and came to be regarded as having utilitarian goals. It is traditionally assumed to start with the Copernican revolution and to be complete in the grand synthesis of Isaac Newton's 1687 Principia. Much of the change of attitude came from Francis Bacon, whose confident and emphatic announcement in the modern progress of science inspired the creation of scientific societies such as the Royal Society, and Galileo, who championed Copernicus and developed the science of motion. In the 20th century, Alexander Koire introduced the term scientific revolution, centering his analysis on Galileo, and the term was popularized by Butterfield in his Origins of Modern Science. Thomas Kuhn's 1962 work The Structure of Scientific Revolutions emphasized that different theoretical frameworks, such as Einstein's relativity theory and Newton's theory of gravity, which it replaced, cannot be directly compared. Significance. The period saw a fundamental transformation in scientific ideas across mathematics, physics, astronomy, and biology in institutions supporting scientific investigation and in the more widely held picture of the universe. The scientific revolution led to the establishment of several modern sciences. In 1984, Joseph Ben David wrote, "Rapid accumulation of knowledge, which has characterized the development of science since the 17th century, had never occurred before that time. The new kind of scientific activity emerged only in a few countries of Western Europe, and it was restricted to that small area for about 200 years. Many contemporary writers and modern historians claim that there was a revolutionary change in worldview. In 1611 the English poet, John Donne, wrote, "The new philosophy calls all in doubt, the element of fire is quite put out, the sun is lost, and thirst, and no man's wit can well direct him where to look for it." Mid-20th century historian Herbert Butterfield was less disconcerted, but nevertheless saw the change as fundamental, since that revolution turned the authority in English not only of the Middle Ages but of the ancient world, since it started not only in the eclipse of scholastic philosophy but in the destruction of Aristotelian physics. It outshines everything since the rise of Christianity and reduces the Renaissance and Reformation to the rank of mere episodes, mere internal displacements within the system of medieval Christendom. It looms so large as the real origin both of the modern world and of the modern mentality that our customary periodization of European history has become an anachronism and an encumbrance. The history professor Peter Harrison attributes Christianity to having contributed to the rise of the scientific revolution. Historians of science have long known that religious factors played a significantly positive role in the emergence and persistence of modern science. In the West, not only were many of the key figures in the rise of science individuals with sincere religious commitments, but the new approaches to nature that they pioneered were underpinned in various ways by religious assumptions. Yet, many of the leading figures in the scientific revolution imagined themselves to be champions of a science that was more compatible with Christianity than the medieval ideas about the natural world that they replaced. Ancient and medieval background. The scientific revolution was built upon the foundation of ancient Greek learning and science in the Middle Ages, as it had been elaborated and further developed by Roman, Byzantine science and medieval Islamic science. Some scholars have noted a direct tie between particular aspects of traditional Christianity and the rise of science. The Aristotelian tradition was still an important intellectual framework by the 17th century, although by that time natural philosophers had moved away from much of it. Key scientific ideas dating back to classical antiquity had changed drastically over the years, and in many cases been discredited. The ideas that remained, which were transformed fundamentally during the scientific revolution, include Aristotle's cosmology that placed the Earth at the center of a spherical hierarchic cosmos. The terrestrial and celestial regions were made up of different elements which had different kinds of natural movement. The terrestrial region, according to Aristotle, consisted of concentric spheres of the four elements, earth, water, air, and fire. All bodies naturally moved in straight lines until they reached the sphere appropriate to their elemental composition, their natural place. All other terrestrial motions were non-natural, or violent. The celestial region was made up of the fifth element, ether, which was unchanging and moved naturally with uniform circular motion. In the Aristotelian tradition, astronomical theories sought to explain the observed irregular motion of celestial objects through the combined effects of multiple uniform circular motions. The Ptolemaic model of planetary motion, based on the geometrical model of Eudoxus of Cnidus, Ptolemy's Almagest, demonstrated that calculations could compute the exact positions of the sun, moon, stars, and planets in the future and in the past, and showed how these computational models were derived from astronomical observations. As such, they formed the model for later astronomical developments. The physical basis for Ptolemaic models invoked layers of spherical shells, though the most complex models were inconsistent with this physical explanation. It is important to note that ancient precedent existed for alternative theories and developments which prefigured later discoveries in the area of physics and mechanics, but in light of the limited number of works to survive translation in a period when many books were lost to warfare, such developments remained obscure for centuries and are traditionally held to have had little effect on the rediscovery of such phenomena, whereas The invention of the printing press made the wide dissemination of such incremental advances of knowledge commonplace. Meanwhile, however, significant progress in geometry, mathematics, and astronomy was made in medieval times, particularly in the Islamic world as well as Europe. It is also true that many of the important figures of the scientific revolution shared in the general Renaissance respect for ancient learning and cited ancient pedigrees for their innovations. Nicolaus Copernicus, Kepler, Newton, and Galileo Galilei are all traced different ancient and medieval ancestries for the heliocentric system. In the Axioms Scholium of his Principia, Newton said its axiomatic three laws of motion were already accepted by mathematicians such as Huygens, Wallis, Wren and others. While preparing a revised edition of his Principia, Newton attributed his law of gravity and his first law of motion to a range of historical figures. Despite these qualifications, the standard theory of the history of the scientific revolution claims that the 17th century was a period of revolutionary scientific changes. Not only were there revolutionary theoretical and experimental developments, but that even more importantly, the way in which scientists worked was radically changed. For instance, although intimations of the concept of inertia are suggested sporadically in ancient discussion of motion, the salient point is that Newton's theory differed from ancient understandings in key ways, such as an external force being a requirement for violent motion in Aristotle's theory.